Superimposition of electrical forces. Many times, there's a configuration consisting of multiple charges, and you need to calculate the net initial force on each charge. The charge configuration will then change as the charges react to their initial net forces, but that is way beyond the scope of this course. The simplest configuration to handle is when the charges are all in a line, for example, on the x-axis. So here we have 3 charges all in a line. Follow this procedure. Assume all charges other than the one that the initial net force is being calculated for are immobile. This will allow the determination of the direction of the individual initial forces. Then, draw a free body diagram for each charge, using the fact that opposite charges attract and like charges repel. Then, use Coulomb's law to find the magnitude of each force. Then, sum the forces, taking into account that they are vectors with direction and magnitudes. So if they point one direction, they'll be positive. If they point the other direction, they'll be negative. Use the free body diagrams to assign signs to the forces. So for example, if they point to the right, they'll be positive. If they point to the left, they'll be negative. Here is the labeling convention. So F12 will be the force that charge 1 exerts on charge 2. F sub 13 will be the force that charge 1 exerts on 3, and F23 will be the force that 2 exerts on 3. So note that by application of Newton's third law, the force that 1 exerts on 2 will be equal to the negative force that 2 exerts on 1 because they're equal in magnitude but opposite in direction. Other textbooks and websites may use a different naming convention. It might be opposite to this one, so it might be F21. Either works, just follow your instructor and stay consistent. Let's now work this problem and find the initial forces on each charge. What's the first step in any force or dynamics problem? Discuss and then check the next slide. That's right, hopefully. Draw free body diagrams for the forces acting on each charge. All right, so here, Q1, we draw our little dot. Now this is a positive charge, therefore this negative charge is going to be an attractive force. So it's going to try to make Q1 accelerate to the right. However, Q3 is also positive, so it will push Q1 to the left. Now we're not worrying too much about the magnitude of these vectors yet. We mostly just care about direction. So Q2 is negative, which means it will be pulled by Q1 to the left and by Q3 to the right. So we have these two forces here. And finally, Q3 has two forces on it. It has a repulsive force from Q1, so that's going to go this way. And it's attracted to Q2, so like that. All right, and here is the fun part. We're going to use Coulomb's law to find the magnitude of the forces acting between each pair of charges. So the force between 1 and 2, the force between 1 and 3, and the force between 2 and 3. So we have K, Q1, Q2 over R squared, and make sure when you're plugging in numbers, you're plugging in the correct numbers. So here is where Q1 is, 25 microcoulombs, which is where we get that times 10 to the negative 6. Q2 is negative 10 microcoulombs. Now that negative sign won't matter because we're using the absolute values. This is just to find the amount of force, not the direction. And then make sure you use the correct distance. So the R value between 1 and 2 is 8. But see, each pair of charges is going to have a different distance. So when you do that, you get your 3 magnitudes of the forces. Now we go back to our free body diagrams. We're going to use them and the magnitudes of the forces that we just found to find the magnitude and direction of the initial force on each charge due to the configuration. So the force on Q1 is going to be the force between 2 and 1 to the right, so that will be positive, And that was this number from the previous slide. And then we have the force between 3 and 1, but that's to the left. So that's going to be negative. And then we use the number from the previous slide to find that overall there is a positive net force acting on Q1 to the right. Because it's a positive number, that means it's to the right. So for Q2, we have a negative force to the left, this magnitude here, but we have a big force to the right, so therefore we end up with about 5 times 10 to the negative 2 newtons to the right. So there's also a net force to the right here, and actually this is larger, so it's like that. And finally, the force on Q3 is going to be big and to the left, so this way.